Welcome to another interesting class of diffusion in multi-component solids. In today's class, we will see some of the features of concentration profiles that develop in a diffusion couple. We will look into both binary and multi-component diffusion couples. Diffusion couple is a very important concept for this class. Throughout this class, we will use diffusion couples for various purposes, particularly for determination of interdiffusion coefficients and to see how the concentration profiles evolve in different types of infinite boundary conditions. So, it is important to go over some of the features of concentration profiles which are developed in infinite solid-solid diffusion couples. We have already derived the solutions to diffusion equation with the boundary conditions as applicable for infinite diffusion couples. Today, we will see how the concentration profiles evolve and what are different features. So, first we will look into diffusion profiles in a binary diffusion couple. So, the concentration at any position x, let us call it C A, concentration of component A at x and t is given by C A plus, which is the concentration of the right side terminal alloy, plus C A minus, which is the concentration of the left side terminal alloy, minus C A plus divided by 2 times 1 minus error function x over 2 root d tilde t. So, we are considering interdiffusion here, and the interdiffusion coefficient is usually denoted by this symbol tilde on top of d. So, d tilde is the binary interdiffusion coefficient of the system that we are considering here. So, we have derived this equation and it has an error function type of solution, and this is the kind of profiles that develop in a diffusion couple, right. So, if you see, this blue curve is the concentration profile of component A and the other curve is the concentration profile of component B. So, this hypothetical diffusion couple was formed by placing an alloy with 80% of A and 20% of B in atom percent on left side and 90% of B and 10% of A on the right side. As you can see, the first obvious feature of these concentration profiles are each concentration profile shows an inverted symmetry. To explain this further, if I consider the particular profile of component A here, and this is the initial contact plane at x equal to 0. If I flip the concentration profile on the left side of this plane and repeat it on the other side, I get the entire concentration profile, right. That is the inverted symmetry. Of course, we have to rescale our concentration axis. So, in this case, to get this inverted symmetry, I have to make C A plus equal to 0, and you can see between C A minus and C A plus this symmetry can be seen, and it is obvious from the kind of solution that we get for constant interdiffusion coefficients. Okay. Remember, first we are considering the case of constant interdiffusion coefficient, and throughout class today for different concentration profiles I will show, we will also assume that the molar volume V m is constant. Towards the end of the class, we will see what happens if V m varies with composition. Okay. So, the first feature is that each individual profile shows inverted symmetry when interdiffusion coefficient is constant. The second feature you can see, we get same diffusion depths on both sides for any particular component. So, for example, if we see component B, on the left side it has penetrated about 35 micron, on the right side also it has penetrated about 35 micron. Moreover, the diffusion depths of both the components are same in a binary diffusion couple on both the sides. And the reason for this is, we know that we have n minus 1 independent fluxes in an n component system, if we consider the volume fixed frame of reference. So, this interdiffusion coefficient d tilde is in the volume fixed frame of reference, and so we have only one independent flux in a binary system, right, which means for constant molar volume, summation of J1 tilde and J2 tilde is 0. So, from this equation it should be clear that if the flux of a particular component, whenever it goes to 0 in a particular terminal alloy, the flux of other component should also go to 0. So, both the components should show the same diffusion depths. Then typically for binary diffusion, there is only one interdiffusion coefficient which characterizes the diffusion behavior of both the components, and this binary interdiffusion coefficient should have a positive value, which means we will not expect any maxima or minima on any of the concentration profiles, which means there would be no uphill diffusion observed in a binary diffusion couple. Now, what happens if I change the interdiffusion coefficients? So, on the right side here I have shown the binary diffusion profile, and now I have taken the value of d tilde to be 4 times the one I used for previous profiles. So, for the first profile we used d tilde equal to 1 times 10 to power minus 15 meter square per second, and this hypothetical diffusion couple was annealed for 48 hours. The second hypothetical diffusion couple, the same couple essentially, but I am now using interdiffusion coefficient as 4 times 10 to power minus 15 meter square per second, and it is annealed for the same time, that is 48 hours. Immediately you can see the diffusion depths have increased. Obviously, from this equation one can recognize that, as already discussed when we derived this equation also, it can be recognized that the diffusion depth varies as root d tilde t. So, obviously, what it means is, if I increase the interdiffusion coefficient by 4 times, the diffusion depth should be doubled, which can be seen if we compare the two profiles here. In the first profile, the total diffusion depth was about 35 plus 35 on both sides, will be about 70 microns. In the second case, the total diffusion depth 70 plus 70 is about 140 microns. If I increase the diffusion coefficient to 4 times, the diffusion depths would be doubled. So, this was the binary diffusion profiles when the interdiffusion coefficient was constant. Now, for constant d tilde value, we can directly use the expression for concentration profiles, which was error function type of expression, which we derived for the infinite boundary conditions. But when d tilde varies with composition, we cannot solve the diffusion equation straight away or analytically. So, but we can solve the diffusion equation numerically with varying d tilde. So, in this slide I am comparing two couples. On the left side I have the same hypothetical diffusion couple with constant value of d tilde equal to 10 to power minus 15 meter square per second. It was essentially the same couple that I presented first in the last slide. And the second, on the right side, these are the diffusion profiles developed in a binary diffusion couple in which the interdiffusion coefficient varies with composition. And how much it is varying? In the left terminal alloy, the diffusion coefficient is 4.1 times 10 to power minus 14 meter square per second. It varies with composition, and in the right terminal alloy, it has the value of 1.2 times 10 to power minus 14 meter square per second. Now, the difference between the two type of profiles when d tilde is constant as against when d tilde is varying is obvious. The first, if we see, the individual profiles do not show any kind of symmetry, which is obvious because d tilde is varying with composition. Also, the diffusion depths are not same on both the side. In the left terminal alloy, the interdifusivity values are higher than the right terminal alloy, and so we will see the diffusion depth is more in the left terminal alloy than in the right terminal alloy, which is also evident from the slopes of the concentration profiles. We can see the gradient in the concentration is shallower in the left terminal alloy and it is much steeper on the right terminal alloy. Then again, since we only have one independent interdiffusion flux in volume fixed frame and when V m is constant, we have J 1 tilde plus J 2 tilde equal to 0. And so, on any side both the diffusing species should show the same penetration depth or same diffusion depth. These diffusion depths are different on either side, but on any given side the two components should show the same diffusion depth. Again, no peaks are observed because we have a single diffusivity characterizing the diffusion behavior of both the components and we have only one independent component and one independent interdiffusion flux. Now, this was about the binary diffusion profiles. Let us see the nature of ternary diffusion profiles. Now, when I say ternary or a 3 component system, I have 2 independent interdiffusion fluxes. So, based on Onsager's formalism of Fick's law, I can write J 1 tilde equal to minus d 1 tilde 3 dou C 1 by dou x minus d 1 2 tilde 3 dou C 2 by dou x and J 2 tilde equal to minus d 2 1 tilde 3 dou C 1 by dou x minus d 2 2 tilde 3 dou C 2 by dou x. So, I have to define 4 interdiffusion coefficients for a ternary system d 1 1 tilde 3, d 1 2 tilde 3, d 2 1 tilde 3, d 2 2 tilde 3. The superscript 3 here denotes that component 3 is being treated as the dependent component. Components 1 and 2 are the independent component. So, the flux of each component 1 and 2 is expressed in terms of the concentration gradients dou C 1 by dou x and dou C 2 by dou x. These are the concentration profiles of the 3 components developed in a hypothetical ternary diffusion couple, which was assembled between 2 terminal alloys. On the left side, the alloy had 10% of component 1, 42% of component 2, 48% of component 3. On the right side, the alloy had 42% of component 2 and 58% of component 3. Components 1 and 2 are being treated as independent components here and component 3 is treated as the dependent component. Again, this simulation was done for constant set of interdiffusion coefficient and assumption of constant molar volume. Because of the constancy of interdiffusion coefficient, again we can see each individual profile shows inverted symmetry. Then the diffusion depths should also be same on both the side for any individual component. And in a ternary case, since there are 2 independent components and the third one is dependent. So, for constant value of V m, we have J 1 tilde plus J 2 tilde plus J 3 tilde equal to 0. Even if one of the flux goes to 0 earlier than the others, then the other 2 should still satisfy this equation, which means at least 2 components should show the same diffusion depth, if not all 3. This is an important point because in ternary there are 2 independent components and the third one is dependent. Now, in this particular couple you can see component 2 has the same concentration on both the sides. Now, if I want to write the flux of component 2, I can use this equation minus d21 tilde dou c1 by dou x minus d22 tilde dou c2 by dou x, and the set of ternary interdiffusion coefficient that was used to produce this profile is written here. The values are in 10 to power minus 15 meter square per second, and particularly for component 2, d22 tilde is the main coefficient which quantifies the contribution from gradient of 2 to its own flux, and d21 tilde 3 is the cross coefficient that quantifies the effect of gradient of 1 on the diffusion of component 2. So, both the independent gradients will contribute to the flux of 2. So, even if there is no gradient of concentration for component 2 to start with, we can still expect some flux, but in this case the profile is still almost flat, and the reason being the cross coefficient d21 tilde is much smaller than the main coefficient d22 tilde 3. It is order of magnitude smaller than d22. So, even though there is a gradient for 1, so in the first term, even though the gradient of 1 is not 0, but d21 is very small, and so the cross effect is negligible here. The gradient of 2 is anyway 0 to start with, and so we get to see almost flat profile for component 2. However, in a ternary couple we may expect maximum and minimum on one or more profiles, which denotes the presence of a field diffusion. We will see that in the later slide, but now let us see what happens if I change the main interdiffusion coefficient. So, in this matrix now, if I increase the interdiffusion coefficient of 1, so now I am keeping the 3 components of the matrix same, but I am increasing the 1 tilde 3, and we can see the diffusion depth of component 1 has increased. Right. In the first couple, where d11 tilde 3 was 4.5 times 10 to power minus 15 meter square per second, the diffusion depth was about minus 72 plus 70, about 140 micron. In the second couple, where d11 tilde 3 is 6.4 times 10 to power minus 14 meter square per second, the diffusion depth is about minus 232 plus 230 is about 460 microns. Right. So, the diffusion depth of component 1 has increased, but you can see the diffusion depth of component 3 has also increased, and the reason being, as I explained earlier, we have to satisfy this condition sigma j I tilde equal to 0, and since j2 tilde is almost 0 throughout the diffusion profile, j1 tilde has to be equal to minus j2 tilde. So, the component 3, which is the dependent component here, responds to the changes in concentration of component 1, and so the diffusion depth of component 3 has also increased. Okay, let us see the effect of cross terms, or how diffusional interactions work in a multi-component system, or how diffusional interactions are important in a multi-component system. On this slide, I am comparing 2 cases of the same diffusion couple, or the diffusion couple formed with the same 2 terminal alloys as described in the previous slide. Now, here what I have done is I have changed the cross coefficients. So, the first profile is same as I presented previously, with main coefficient d11 tilde equal to 4.5, d22 1.7, d12 3 and d21 minus 0.6. The values are in 10 to power minus 15 meter square per second. For the second case, I kept the main coefficient same, but increased the cross coefficient d tilde to 1 to minus 4 times 10 to power minus 15 meter square per second. So, I have increased the magnitude of cross coefficient d21 tilde by an order of magnitude. Now, in order to keep the matrix positive definite, I had to decrease the value of d12, but let us see the effect of this change in magnitude of cross coefficient of component 2. In the previous case, since the cross coefficient was very small and we started with the same concentration of 2 on both the terminal alloys, we saw that the concentration profile for component 2 was almost flat. But now, since the cross coefficient has considerable magnitude, in fact, the magnitude of cross coefficient here is higher than that for the main coefficient d22 tilde 3, and it gives rise to this kind of maximum and minimum in the concentration profile. In other words, component 2 is showing uphill diffusion, because now the interactions are very strong, which is reflected in the large magnitude of d21 tilde 3. Now, the cross coefficient can be negative or positive. In this case, I considered negative cross coefficient. What if the coefficient was positive? In this slide, I am comparing two cases again. In the first case, coefficient of 21 is negative, whereas in the second case it is positive. And if you compare the two concentration profiles, we can see the concentration profile of 2, its maximum and minimum. The positions of maximum and minimum on concentration profiles of 2 are flipped as I change the sign of its cross coefficient, right. In the first case, the maximum was on the left side, whereas minimum on the right side. In the second case, minimum is on the left side and maximum is on the right side. Now, it has also affected the concentration profile of component 3, right, because not all concentration gradients are independent. So, we can write dou C1 by dou x for constant molar volume plus dou C2 by dou x plus dou C3 by dou x equal to 0. So, if I am treating 1 and 2 as independent component, 3 is the dependent component. So, if the gradient of 2 changes, and you can see there is not much change in the concentration profile of component 1. So, the concentration profile of dependent component 3 also has to change in order to satisfy this equation. So, this is how the diffusional interactions can give very interesting concentration profiles, and these diffusional interactions are quantified in terms of the cross coefficients. Now, let us see what this negative and positive signs mean, right. So, for example, if I write the equation for component 2, if I write the equation for interdiffusion flux of component 2, now we can see the contribution is from both the main term, which is this d22 times dou C2 by dou x, and the cross term d21 times dou C1 by dou x. Now, let us suppose d22 is positive and the concentration gradient to start with is negative. So, the second term in effect is positive, right. Now, if d21 tilde is negative and the gradient term of 1 is also negative, which is the case here, then the first term becomes negative, right, and it is decreasing the flux of component 2. So, or it has a reducing effect, because the second term is positive, the first term is negative, which means the interdiffusion flux of component 2 is reduced down the gradient of 1 and it is enhanced up the gradient of 1. How is it enhanced? Up the gradient. Up the gradient means if by any chance in a couple, if the gradient of one was positive, then this total first term will be positive and it will add to the second term, and so it has an additive effect. That means, the negative value of cross coefficient d21 tilde 3 enhances the interdiffusion flux of 2 up the gradient of 1 and reduces down the gradient of 1. With a similar logic, if d21 tilde was positive, it would have reverse effect. The positive value of cross coefficient d21 tilde 3 means the interdiffusion flux of 2 is enhanced down the gradient of 1 and reduced up the gradient of 1. Okay. So, this is how the diffusional interaction can affect the concentration profiles in a multi-component system. Now, let us look into some of the real multi-component concentration profiles. I will give you a couple of examples. The first one is an iron nickel aluminum ternary diffusion couple taken from this reference here by Dayananda and so on. Profiles are plotted by extracting the data from this reference. You can see in this particular couple between two iron nickel aluminum alloys, the aluminum profile is characterized by very prominent maximum and minimum. Also, the iron profile is characterized by a very prominent maximum here on the right side of the initial contact plane, or what it is also referred to as metanoplane, which means strong diffusional interactions exist in this iron nickel aluminum system. So, this particular couple was diffusion annealed at 1000 degree centigrade for 48 hours. As we see, the prominent maximum and minimum on aluminum and the prominent maximum on the iron profile, and this indicates strong diffusional interactions in this system. And this was actually evidenced in terms of large values of cross interdiffusion coefficient in this system as reported in this reference. Particularly D nickel aluminum and D aluminum nickel here are very highly negative. So, they are negative and have large magnitudes. This is another example. This is in a quinary diffusion couple. In fact, two diffusion couples I am showing again from this reference recently published in JMR. The first couple was assembled between a quinary alloy. Quinary means 5 component system. On the left side we have 40 iron, 23 nickel, 17 cobalt, 23 chrome, 23 manganese. The concentrations are in atom percent. And the right side 26 iron, 17 nickel, 23 cobalt, 17 chrome and 17 manganese. And these are the concentration profiles developed in this quinary diffusion couple. And important to note here is the nickel profile. You can see a nice maximum here on the left side and there is a minimum on the right side of the initial contact plane here. Similarly, in the second diffusion couple, which was assembled between 14 iron, 17 nickel, 23 cobalt, 23 chromium, 23 manganese and 26 iron, 23 nickel, 17 cobalt, 17 chromium, 17 manganese, the concentrations being in atom percent. On cobalt profile, we can see a maximum and minimum here, and this indicates the presence of strong diffusional interactions in this system. This particular system, iron, nickel, cobalt, chrome, manganese, is a very important system. It has recently gained lot of importance, particularly in high entropy alloys, in which diffusion is one of the most debated topics. And these couples actually show there exist strong diffusional interactions in high entropy alloy systems, particularly this one, iron, nickel, cobalt, chrome, manganese. If you want more, you can refer to this paper. We have also characterized the interdiffusion coefficients. A quinary interdiffusion coefficient matrix has n minus 1 square 4 square. So, 16 terms, or a quinary composition is characterized by 16 interdiffusion coefficients in volume fixed frame of reference. Okay. So, these are some of the examples of multi-component diffusion couples and the concentration profiles developed in these couples. Now, as I said, for all the discussion so far in this class, we assumed molar volume is constant, because we used for many of the profiles we used the analytical expressions derived by solving the diffusion equation, which was dou C I by dou T equal to minus dou J I tilde by dou x. Now, if molar volume is not constant, then this J I tilde, which is basically the flux in volume fixed frame of reference, can be expressed in terms of the flux in stationary frame of reference as J I 0 minus C I times u v, where u v is the velocity of the volume fixed frame with respect to stationary frame. Now, whenever I write this continuity equation, you have to remember the flux here is in stationary frame of reference. The continuity equation applies for the stationary frame of reference. So, if I have to solve this equation, I have to substitute in terms of the volume fixed frame of reference as J I tilde v plus C I times u v. If u v is 0, which is the case when molar volume is constant, then you can see the volume fixed frame and the stationary frame would coincide, or the fluxes determined in any of the frame would be same. And so, we can directly substitute here and solve this equation. But if u v is not 0, which is the case when molar volumes vary with composition, more specifically when partial molar volumes vary with composition, then we have to account for this term u v, and again u v is also function of x, and so this becomes a complicated equation to solve, right, and then this equation cannot be solved straight away, and that is why we assumed the molar volume was constant, so that we can simplistically show some features of the concentration profiles using the analytical expressions. Of course, for varying case of binary interdiffusion coefficient, we solved the diffusion equation numerically, again for constant molar volume case. Okay. So, I think that should be all for now. I will explain in more detail what happens if, or how we solve for u v when the partial molar volumes are not constant, but that will come later in the class.